This video is going to be the first in a three-part series looking at simultaneous equations. This video we're going to be looking at a system of linear equations, so two linear equations, and we're going to be solving them simultaneously. Video number 2 we're going to be looking at the case where we have one linear equation and one quadratic equation, and then video 3 we're going to be looking at the case where we have one cubic equation and one quadratic equation. So this can be quite tricky. So this first video we're going to be looking at the case where we have two linear equations. This is it's a relatively basic part of A-level maths, and it is something that you should have covered at GCSEs, but nonetheless the techniques and the steps involved, regardless of whether you're looking at two linear equations or the harder example where you're looking at a quadratic equation and a linear equation, your steps involved and the thought process is going to be exactly the same, but obviously algebraically the more difficult the question, the more difficult the manipulation required. So I'm just guiding you through the general structure of this video. The first, it's going to be split up into two parts. So the first part is going to be guiding you through step by step, just through one example of solving simultaneous equations, and then part 2 is going to be more big picture. So I think this is very important because these are the concepts and these are the ideas that you want to be thinking about when you're going on to solving the harder types of questions, and then we're also going to be graphically showing you the intuition behind what we're actually doing here. So the equation that we're going to be looking at is, the system of equations that we're going to be looking at is going to look like this. So we have the first one, 3x plus 2y, so I'm going to make that 5y equal to 8. The second one is going to be 6x plus 2y equal to 4. Right, straight away, you should know that there are two different methods of solving simultaneous equations where both equations are linear. You can either solve this system of equations by elimination. So if you're looking at the two equations we've got here, you notice my coefficients on x here is 3, my coefficient on x here is 6. So what you could do is multiply this first equation through by 2, which will give you something that looks like this. Okay, so just multiplying all of my terms in that first equation there by 2. And now here, my coefficients match up. So I've got 6x, 6x here. I can simply subtract this equation away from this equation, and then that will leave me with an equation y. Essentially, I would have eliminated my x variable, and then you can solve it that way. We're not going to do that. We're going to solve our simultaneous equations by substitution rather than elimination. The reason why I say this is that although at GCSE it probably is easier to solve simultaneous equations by substitution rather than elimination, once you get to A level, you can actually solve every single type of simultaneous equation using the substitution method rather than the elimination. So in terms of approaching the exam with stuff to remember, if you always remember to solve when you're presented with a set of simultaneous equations to solve, if you always remember to solve it by substitution, which is what we're going to do here, rather than elimination, then it just kind of simplifies the thought process going into the exam. So solving by substitution, your first step, okay, so there are 3 steps involved. Your first step, you need to make one variable the subject of its equation. Number 2, you're going to substitute in the resulting expression into the other equation, and then you're going to solve for one variable. And then step 3, you're going to find the other value in the coordinate pair. What this looks like in practice. Okay, so we've got these two here. First step, we need to rearrange either one of these equations such that either x or y is the subject of that equation. So it doesn't matter, you could pick this first one here, you can make x the subject of the equation, or you could pick this one here and you can make y the subject of the equation. You could pick this one, you can look at the second equation and you could pick either x or y and make that the subject of equation 2. So let's just go for this. So I'm going to look at equation 1 and I'm going to make x the subject here. How do I do that? Well, I'm going to start off by subtracting 5y from both sides. So the left-hand side becomes 3x, right-hand side becomes 8 minus 5y. And then, second of all, divide 3 by 3. So x equals 8 over 3 minus 5 over 3y. Okay, so that's the first step. I have now made x the subject of this equation, i.e. x is by itself on one side of the equation. Now, step 2, I need to substitute this expression into my equation 2. Okay, so I'm going to put 1, the rearranged form that is, of equation 1, into equation 2. So substituting in, that's where the substitution comes in. So what does this look like? Well, all I'm going to do, every time I see an x in this equation here, I'm going to replace it with this expression here, but leave it in brackets. Okay, so I've got 6. Okay, instead of x, I'm just going to put the right-hand side of that equation up there, up here, into here. So 6 lots of effectively my x, plus 2y equals 4. And you notice here now, now that I've substituted in the expression here, the rearranged form of this equation into my second equation, I now have an equation involving only one variable. Okay, so essentially my x has disappeared from this equation here, and now I can solve this. So this is always the case, regardless of whether we're looking at a quadratic and a combination between a quadratic and a linear equation, or you're looking at a combination between a cubic and a quadratic equation. Once you get to this step here, once you've rearranged and you substituted one equation into the other equation, you should be left with an equation involving only one variable. Okay, next step, we need to solve this. So I'm going to expand my brackets to begin with. So just multiplying each of these two terms here by 6. So effectively I have 48 over 3 minus 30 over 3y. So just remember, when you're multiplying by a whole number, the denominator stays the same, but I'm just going to multiply this whole number here by the numerator. So 6 8s gives me 48, 6 5s gives me 30, and obviously the denominator stays the same, plus 2y equals 4. Okay, let's start off by tidying up my y terms. So we can do this in 2 steps, really, can't we? So I have minus 30 over 3y. So I'm just going to gather my y terms on the left-hand side, my number terms on the right-hand side. So I'm going to subtract 48 over 3 from both sides, like that. Okay, gathering together my y terms, I've got minus 30 over 3y plus 2y. Oh, okay, that's come out quite nicely. I just made this example up, but it's come out quite nice. So I've got minus 30 over 3 gives me minus 10y there, plus 2y. So I have minus 8y altogether on the left-hand side. The right-hand side, this also comes out quite nicely as well. Oh, that's fantastic. So 48 over 3 gives me 16. So I've got 4 minus 16, which gives me minus 12. Okay, dividing through, y equals minus 12 over 8, or you can see, minus 12 over minus 8, so dividing both sides by minus 8 there to get my y by itself on the left-hand side, which is just the same as 12 over 8. Okay, negative divided by a negative gives me a positive, which is the same as 3 over 2. Okay, so just simplifying that fraction, actually 4 goes into 12 3 times, 4 goes into 8 twice. Okay, so that's my y variable found. So that's step number 2. I've substituted in my rearranged form of equation 1 into equation 2. I've solved for my first variable. If you rearrange this such that you made y the subject here, then once you got to this step here, you'd have an equation just involving your x variable, and you'd be solving for your x variable down here. Now, so we found our y variable. So remember, with simultaneous equations, you're starting off with a system of equations involving both x and y. Your objective is to find, essentially solve both of these equations simultaneously and find a set of values, so a value for x and a value for y, which satisfies both of these equations simultaneously. So we found our y value, we now need to find our x value. I'm going to do that. Okay, I'm going to window this and make everything a bit smaller. Okay, so we've now found our y value. We need to find our x value. How do we do that? Okay, we've got y equals to 3 over 2 here. I can choose any one of these equations to substitute my y value into, and then I can solve that to get my x value out. So it doesn't matter whether I choose this one, this one, this one, this one. And remember, because in this first step I've solved both of these equations simultaneously, whatever y value, whichever of these equations I plug my correct y value into, it will give me the correct x value. So let's just pick the top one for simplicity. So I'm going to say y equals 3 over 2 implies, okay, 3x plus 5 lots of my y, and in this case my y is 3 over 2, is equal to 8. Okay, solving that, 3x plus, similar to here where I just expanded out those brackets, i.e. multiplying my whole number by my fraction there, 3x plus 15 over 2 equals 8, and then solving 3x equals 8 minus 15 over 2. Okay, so fractions here, 16 over 2 minus 15 over 2. Okay, so 3x equals a half. Right, so my x equals a half divided by 3, i.e. 1/6. Okay, so just if you're struggling with your fractions and your manipulation of fractions, this is on a cheat sheet on my website, so be sure to take a look at that. But essentially here, dividing a half by 3, that half needs to become 3 times smaller. What's 3 times smaller than a half? It's a sixth. There are a multitude of different ways to look at dividing a fraction like that. Okay, but now we have our two solutions. So this is fully solved. I have a solution for my y value, a solution for my x value. I have solved these simultaneous equations together. Okay, and that's the objective of questions like this. Okay, so just a quick note on the system of equations we had previously. This first set here. If you notice here, neither my x or my y is the subject of the equation, so we needed to make x or y the subject of the equation before we substituted one into the other. Okay, so that was our first step here, made x the subject of the equation, and we substituted in place of our x in the second equation here. You notice here, if we were presented with this set of equations to begin with, then you could simply just substitute in place of your y in this first equation here, so no rearranging required. And then if we're presented with a set of equations here that look like this, again, you can see that y is the subject of this equation, y is the subject of this equation, and then you're simply going to set one equation equal to the other, i.e., again, you're going to replace your y in this equation here with the expression that's equivalent to y in this second equation here. In other words, okay, so taking that first equation, we have 8 over 5 minus 3 over 8x on the right-hand side. On the left-hand side, 6x minus 4. Okay, so just replacing this y with this expression for y on the left-hand side of this first equation there. So essentially this principle is quite important when you go on to look at more difficult examples. Just saying, any time you're solving simultaneous equations, essentially you need to substitute in one an expression equivalent to one variable into the other equation. Okay? But sometimes it will be a little bit more complicated in that you'll need to isolate, you'll need to make x or y the subject of one of these equations, but other times it will be more straightforward like this, and you can just actually really set one equation equal to the other, or one side of one equation equal to one side of the other equation there. Okay, so just taking a bit more of a big picture overview now. What we were presented with was a system of linear equations like this: 3x plus 5y equals 8, 6x plus 2y equal to 4. Okay, we had a system of linear equations, i.e. more than one equation, with a system, and our system consisted of two equations in two unknowns. So we've got equation 1, unknown 1 is x, unknown 2 is y. Equation 2, again, x and y. So a system of linear equations, a system of two equations in two unknowns. And because we have two equations and two unknowns, we can actually solve for x and we can solve for y. Whereas if I had, if I changed this and introduced one more variable here, plus z equal, so all I'm doing is adding in one more variable. You cannot solve for numerical values in this system of equations because I have more unknowns than equations. Okay, for me to be able to solve this, I have three unknowns, I would need a third equation. Something that looks like that. Okay, and then you can solve for your x, for your y, and for your z in this system of equations. This is something you would never look at a system of three linear equations in normal A-level maths, so don't worry about this too much. If you do go on to study a quantitative-based subject at university, this is the type of thing you'll be looking at quite a lot. So that's the first point I wanted to make. The second point I wanted to make is regarding what we're actually doing here intuitively and graphically. So we had 3x plus 5y equal to 8 and 6x plus 2y equal to 4. And some of you would be able to recognise that these are actually the equations of a straight line. So just put this in a more recognisable form. So I'm going to make y the subject of each of these equations. So we can have 5y equals 8 minus 3x, or y equals 8 over 5 minus 3 over 5x. Okay, and then just rearrange this in the form y equals mx plus c. I'm just going to put my term in x at the front. Okay, so here, equation of this line in the form y equals mx plus c. Here you can see that my gradient of this straight line is minus 3 over 5. My y-axis intercept is 8 over 5. Let's do the same thing for equation number 2. Don't need to do that. Equation number 2, so I've got 2y equal to 4 minus 6x, y equal to, dividing 3 by 2, 2 minus 3x. And then just putting that in the form y equals mx plus c. So there you can see that my y-axis intercept in this case is going to be plus 2, and my gradient of this line is going to be minus 3. Right, so what we're doing when we're solving these simultaneous equations, so just think back to, let's just think back to the answers that we got. So here we had an x coordinate of 1/6 and a y coordinate of 3 over 2. So x coordinate of 1/6 and a y coordinate of 3 over 2. Okay, so if I was to graph both of these, I'm going to sketch it rather than graph it properly. So my first straight line here, y equals minus 3 over 5x plus 8 over 5. So we'll call this 8 over 5 here. Minus 3 over 5x, so if I'm sketching this, it's going to be a downward sloping straight line with a gradient less steep than 1, so quite shallow curve like that. And then this line here, plus 2, so it's going to start at a slightly higher point. Call that 2. And it's going to be minus 3x, so my gradient is going to be slightly steeper than this straight line here. Okay, and where these two lines cross, this point of intersection, that's going to give you the solutions to your simultaneous equation, i.e. if you compare this point here on the graph to these coordinates, so you can see that my x value 1 over 6, my y value 3 over 2, they're both positive. Obviously I haven't sketched this very accurately, but you can see in terms of order of magnitudes this kind of looks correct. So my x coordinate is positive, my y coordinate is positive, so it's going to be in this quadrant here, and my two lines, they do indeed meet in this first quadrant. This is quite an important concept, so anytime a question asks you for points of intersection between two lines, or they say, they ask you for points of intersection between these two equations, then well, you need to solve them simultaneously. You need to be thinking of simultaneous equations. I need to get a value for x and a value for y. In this case, when you have two linear equations, it's quite straightforward. You're only going to have one value of x and one value of y, one value of x and one value of y, corresponding to one point of intersection like that. This will pretty much always be the case when you have two linear equations. The only time when you're not going to have one point of intersection between two straight lines is if the two lines are parallel, like that. But you won't encounter that. They won't give you two linear equations like that in the exam. But like I said, this is a very important concept when it comes to the harder types of questions. So you're thinking simultaneous equations, points of intersection. For linear equations, you're going to just have one point of intersection, but for if one of these equations is quadratic or cubic, then this is going to change your result quite significantly. Thanks very much for watching, and don't forget to subscribe for more tutoring videos. Remember that full notes and other resources are available on my tutoring website at idktuition.com. And if you'd like me to cover anything in particular, please leave me a message in the comments below or on Twitter at TomDavies32.